In this video, we'll continue talking about the Dirac delta function, and we'll see how it works with Laplace transforms. So just as a quick recap, the delta function was a model for a really quick, almost instantaneous impulse, a force, just a quick hit, such that the overall impulse was equal to 1. So sort of as a function, the delta function is equal to infinity at this one point, but 0 everywhere else. But its integral ends up just equaling 1. And we saw delta as the limit of a bunch of rectangles, all of whose areas were equal to 1, but they were getting skinnier and taller, skinnier and taller. And this is sort of the limiting case of that process. And then this really nice property is that when you integrate a delta function times any other function, f of t, it's just equal to f of a. All right, so we're ready to figure out what the Laplace transform of a delta function is, and it could not be simpler. So the Laplace transform of delta a of t. Well, back to the drawing board. Definition: integrate from 0 to infinity delta a of t, and you're supposed to integrate times e to the minus st dt. Well, it's immediate. It's immediate if you remember this property. Anytime it said you're integrating delta times something, just plug that a into this function, and that's your answer. So here we just plug the a into this function, and that's our answer. I'll put the a first, e to the minus as. So that's the Laplace transform of the delta function. And again, just to distinguish, let me remind you that the Laplace transform of the Heaviside function was similar but not the same. It was e to the minus as over s. So they're similar, but not quite the same thing. So let's try this out and have us solve a second-order linear constant coefficient differential equation where the forcing term now is just a real quick whack at time t equals 5. So just a delta function, just a sudden hit at time 5. So the idea here is, if this were a mass on a spring, let's see what the actual physical nature of this problem would be in that case. So we would have a mass on a spring, and based on these initial conditions, right, we're stretching it out to 2, and then we're just letting it go. We're not giving it any initial speed. So we're bringing it out here, and we're letting it go. And for the first 5 seconds, that's it. There's no other force. So this thing, as you would expect, well, it actually depends on the damping term, right? But it looks like, I think this one is going to be underdamped, so this one would oscillate back and forth. And we can and sort of will figure that out, sort of its natural frequency and all that. And that's how it'll go for the first 5 seconds. But then, right at t equals 5, wherever it is, we're going to give it a real quick hit, an instantaneous hit. And this is a 1 delta t, so that's a positive one. So we're going to hit it in the positive direction with an impulse of 1. So wherever it is, we're just going to boom, hit it to the right. So like if it was going this way, then that'll give it a more of a push that way. If it was going against us, if it was going to the left and we hit it that way, it could certainly slow it down, or of course make it go back the other way. So that's what we're talking about. We're talking about a sudden hit to the right in the positive direction, an impulse of 1. And how will it behave after that? So sort of amazingly, we're going to just solve this all at once, and it's going to have the first 5 seconds going back and forth, and then also what happens after, well, there is no during the hit, but during and after the hit, what it will do after that. So our Laplace transform method is just going to do all this for us all at once. Okay, so it's the same approach. It's just now we know what the Laplace transform of the delta function is, and we work it all out. So let's give it a try. We take the Laplace transform of both sides. So on the left we'll get, that would be for the second derivative. Notice y prime of 0 equals 0. Sorry, that term isn't there. It's minus 0. Plus 2 times s y of s minus 2. Plus 26 y of s. And then on the right side, the Laplace transform of delta sub 5 is just e to the minus 5 s. All right. So now we do our usual thing, right? Laplace transform has turned this into an algebra equation, so we solve the algebra equation for y of s. Feel free to pause and or follow along on your own, but I'll do this slightly quickly. Looks like that after some grouping. And then when we move things around over to the other side, we're looking at that. Okay. Now, normally at this point we would try partial fractions, but I think we're going to find that partial fractions won't really do anything for us. The s squared plus 2s plus 26 is not factorable. Your b squared minus 4ac is negative here, so this just doesn't have two real roots. It can't be factored, and therefore the partial fractions, we can't decompose this into separate fractions with linear denominators. It just won't work. So what that means, and it's not a surprise actually, is that we're just going to have to live with the quadratic, and so it's going to be cosine and sine. When you have a quadratic down here, right, that's on our Laplace transform table, that corresponds to cosines and sines. Or at least it does if we didn't have this 2s in there, but we can force that by doing completing the square process. So s squared plus 2s plus 26 would be s squared plus 2s, and to complete the square I need a plus 1, right, half of this squared, and I steal 1 from the 26, and then I have plus 25, so s plus 1 squared plus 25. So that's how this denominator is going to be, the square will be completed. Let me just do that for all of them now. Okay, there we go. And so now the denominator is looking more like cosine, what we need for a cosine and a sine. It's just shifted to the left by 1 in both cases. Okay, well, let's see. I need this s to also be an s plus 1. We need all the s's to be shifted by the same amount. So I can force that as well, right? I can do s plus 1. So that's, because that's in parentheses, I've basically added 2 that I shouldn't have. So I should take 2 away. But notice I still had a plus 4 there anyway. So I think that balances. That's the same as this, if you check it out. Can I just erase this? Minus 2 plus 4, that's just plus 2. So that is the same as that, but in a form that's more useful to us. Okay, and then this guy. Okay, so now for this piece, this part of it, that's going to end up giving a cosine, and then the other one is going to give a sine with the constant, the one without the s. So let me just break that up. Okay. And I think now we're ready to do the inverse Laplace transform for real. So here we go. Y of t. Okay, so here, without the plus 1, this would have been, well, there's a 2. This would have been cosine of 5t. Notice omega is 5 because that's 5 squared right there. Okay. But with the plus 1, we use the s shift rule. The s has been shifted to the left by 1, so a negative 1. And the effect of that in the inverse Laplace transform is to throw in an e to the minus 1t. So that's using the s shift rule. Okay. Now, this guy. We have just a constant here, so that's looking like it should be a sine. And it will be a sine. The only thing is, for the sine, we have omega squared here. We need omega here. Omega is 5. If this is 25, that's omega squared, so we need omega to be 5. So what I can do is put in a 5, and of course divide by a 5, just to force it to happen. So I have a 2/5 sort of leftover constant, and then the 5 over this denominator is a perfect match for sine. So it's sine of 5t. But again, notice it was shifted to the left by 1. So that's going to throw in an e to the minus t. Okay. Finally, for this last term, we're going to be using both shift rules. So let's first just look at the, let's put the exponential off to the side for a second and just focus on the fraction. That by itself, well, that's a lot like the one we just did. Again, we're going to need a 5 up here. So let's make it a 1/5 times a 5. So we would get 1/5, and then it would be a sine of 5t. The fact that it was shifted, again, gives us an e to the minus t. But now, how do we take into account the e to the minus 5s that was multiplying this whole thing? That's the t shift rule, and that means we have to multiply by a u5 of t, and we have to shift what we already had by 5 to the right. So I got that, and I'm going to need to make a little bit of room. That. Okay, let me just rewrite that, make it look nice. And there it is. So we see that what we get as a solution is, okay, this piece is there from the beginning, and this is, well, this is your typical cosine and sine, right? This is typical oscillations, but times an e to the minus t, so oscillations that are dying down. But then, right, we get this heaviside function. Suddenly this turns on at time 5, and of course that corresponds to right when this mass on the spring got whacked. And suddenly this guy happens as well. This gets added on to what this one was already doing. Hard to draw just by looking at the formula here. But here I'll graph what it really is doing. Now what you're seeing so far is just that first part. I haven't put in the part that has the heaviside function. And you see that starting at time 0, notice the initial conditions are matching. It's starting at 2. And the initial condition was that it had a 0 velocity. You see we have a derivative of 0 there. We're at the top of a hill. And yeah, there's the up, down, right? Damping. The e to the minus t is making it go lower, lower, lower until here. But now here, we're not seeing what really happens yet. But there we are. Now, and by the way, I just figured out how to make it stop at time 5, so I'll show you that. So here it goes, right, what we were just seeing, but now it stops right there. And now I'll put in the rest of it. And there it is. So now this graphing utility is graphing the whole thing. So you see at time equals 5, so it had really died out, but then here's the hit, boom. Let me zoom in on that a little bit more. There we go. So yeah, you see the dying out. Now right at time equals 5. Now notice it was actually on the positive side of things. Why is positive here? Not a lot, but it's on the positive side. And remember that what we're modeling here is a push, an impulse of size 1 in the positive direction. So it was already on the other side. It was actually kind of coming to a stop and was about to come back down, it looks like. But right at that moment we hit it, we gave it a little jolt. And so boom, and it goes up, and now it's going to, of course, it's going to oscillate now more. We breathed a little life into it, but it's going to die out again because of the damping. And remember, like after this one moment, there's not going to be any more force. This is a one-time instantaneous force, and we're seeing it right there. And so, yeah, I typed that whole function in as a piecewise defined function into the graphing utility, and this is what we got. So pretty neat. So we're seeing the the effect of that little whack right there. I'm thinking I should just mention one more thing. You would probably figure this out, but how I entered this function into the graphing utility, and you could even do this on the TI-89s and TI Inspires. They don't have heaviside functions per se, but we can get this to work. Right? We can enter piecewise defined functions. So it is equal to just this for t less than 5, right? And then, right now u5, this turns on. So after time 5, it's the whole thing. It's this term plus this term plus this term. And I don't have to write the U5 because remember, that's just 1 once you get past 5. So that would look like, okay, that part again, plus, and now I'm going to write this part. So plus 1/5 e to the minus t minus 5 sine 5t minus 5. Squeeze it in there. Okay, so it comes out nice and succinct in one line when we work with Heaviside functions, but this is how you could enter it into something that will graph it for you.